Hello students, so let's start with the revision of chapter 11 work and energy. We'll have quick revision in this session. Now let us first see what is work. So work formula is W is F into S, where W stands for work and F stands for magnitude of force applied and S for displacement's magnitude. So we have work done is defined as a product of magnitude of force applied and magnitude of displacement produced in the direction of force applied. Now, let us see the SI unit of work. The SI unit of work is Joule, and when we see the formula W is F into S, by putting the SI units of F and S, we get 1 Joule is 1 Newton meter. From this, you can also define, from this equation, you can define the SI unit. Now, work done is said to be 1 Joule when 1 Newton of force is applied and 1 meter displacement is produced in the direction of force applied. Similarly, we can have the Cgs unit of work here. Cgs unit is erg and we can define it in the same manner. So we have from this equation, we have 1 erg is equal to 1 dyne centimeter. Work done is said to be 1 erg when 1 dyne of force is applied on a body and displacement produced is 1 centimeter in the direction of force applied. Now let us see factors on which work done depends. Factors on which work done depends. We know there are 3 factors: magnitude of force applied, magnitude of displacement produced, and this theta is angle between force and displacement. Depending upon these 3 factors, we have 3 different types of work. Let us see. So the first type of work that we are going to see here is positive work. Positive work, I have written here in short, I have shown here that force and displacement when they are in the same direction. So positive work is said to be done when force and displacement are in the same direction. Negative work is said to be done when force and displacement are in the opposite direction. As shown by the arrows here, there are 2 cases shown. Say in the upper case also force and displacement are in the opposite direction. In the lower case also the force and displacement are in the opposite direction. Zero work. Zero work, we know that cos theta, cos 90 degrees 0, and here, so zero work is said to be done when force and displacement are perpendicular to each other. So simply I have given you the 3 definitions for these 3 works: positive work, negative work, zero work definitions we have discussed. You know that for zero work, there are 2 different more conditions. One is when force applied is 0, one is what displacement produced is 0. So when either or both of these conditions are true, then also the work done is said to be 0. Example for positive work, you know, when we pull a drawer to open it, work done is positive when it gets opened actually, when the drawer comes out. So when we pull the drawer and open it, positive work is done. Work for negative work, we can remember work done by frictional force is always negative. Work done by brakes applied or braking force applied on any vehicle is always negative. Zero work. Zero work, we can remember that in case of uniform circular motion, work done by centripetal force is always 0. You know the case? Because this is a case where the displacement is along the tangent and the centripetal force is along the radius towards the center. So they are perpendicular, so work done is 0. Now, let us see what is energy. Energy is defined as the capacity of a body to do work, and it is just like work, it is equivalent to work. Work and energy both are scalars and they have the similar units. So SI unit of energy is Joule and CGS is erg. You can define 1 Joule energy as the energy required to do 1 Joule of work. And similarly, we can define 1 erg also. Now there are different forms of energies. We know energy exists in different forms, but here we are going to derive expressions for kinetic energy and potential energy. So for both the derivations, you have to start first with the introduction. And we can see the steps which are shown here. So accordingly, the introduction should be there. So in case of kinetic energy, you can introduce all these terms involved. So you can write, consider a body having mass m, moving with uniform velocity u on the horizontal surface. Let a constant force F be applied on it for some time. So that A is the acceleration produced, V is the final velocity, and S is the displacement covered in that time. Now, you may mention that the body is initially at rest, or you may mention it later if the body is initially at rest. Okay? So this you can do it in the introduction itself, or you can choose a step later. Now, on the right hand side for potential energy, you can just consider, you have to introduce these terms, mgh. So you will find here, you will write here, consider a body having mass m lying at rest on the ground. Let a constant force F be applied on it to lift it to height h. You have to write here that minimum force required to lift a body up is equal to its weight, and weight of a body is mg. So force required is mg, s is h. So in this case, W is the work done to lift the body up. So W is mgh. This work done is stored in the body as its potential energy. You have to write the sentence, and then potential energy EP is mgh. For the kinetic energy, after writing introduction, you will write work done by the force. W is equal to F into S. Using Newton's second law, F is ma. Using third equation of motion, S is v square minus u square upon 2a. You put these two values, expressions here, substitute for F and S, and then a gets cancelled. So you're left with W is half m in the bracket v square minus u square. We can write here, I have not written, but you need to write that if initially the body is at rest, u is 0. So you putting u as 0, work done is half mv square. This work done is stored in the body as its kinetic energy. So kinetic energy Ek is half mv square. Now the last term here is power. Power is defined as rate of doing work. So power of a body is defined as its rate of doing work, or rate of consumption of energy. So formula for power is P is W over T or E over T. So work done in unit time or energy consumed in unit time is called as power of the body. It is a scalar quantity with SI unit watt. 1 watt we can see from the equation is 1 joule per second. So we can define 1 watt is the power of a body which does 1 joule of work in 1 second, or which consumes 1 joule of energy in 1 second. Now the commercial unit of electrical energy is kilowatt hour, and we can define kilowatt hour or 1 kilowatt hour as the electrical energy consumed when an appliance having power of 1 kilowatt is used for 1 hour. So we can also show the conversion between electrical energies SI unit and commercial unit. So by writing by writing P is equal to E upon T, E is P into T. So here P is 1 kilowatt, R is 1 hour, time is 1 hour. We can write 1 kilowatt hour, we can show is equal to 3.6 into 10 raised to 6 joules. And the last thing, the only topic left is law of conservation of energy. We know the statement of this law. This law states that energy can neither be created nor be destroyed. It can only be converted from one form into another form. So we have done the quick revision of this chapter. I hope you can recall all the topics, definitions, derivations, units. The chapter is very simple. Just remember that if you consider this chapter to be very simple and do the revision, I don't think so you should have any problem in giving the exams. So goodbye students, see you.